As So let's start. And today we are happy to have Gus Schrader from Northwestern, and the title is Skeins, Clusters, and Wave Functions. Gus, please.
Okay, thank you very much, Jan, for introduction and for inviting me to speak in the seminar. So yeah, the title of my talk is Skeins, Clusters, Wave Functions, and it is the things I'll be talking about are based on a couple of joint projects involving collaborators Mingyuan Hu, who's a graduate student here at Northwestern, Lin-Hui Shen from Michigan State, and Eric Zaslow, also here at Northwestern. So the projects kind of consist of currently of two preprints from last year, one called Chromatic Lagrangian, the other with the same title as this talk. Relatedly, I'd also like to mention very closely related work by Matthias Scharzer and Vivek Shende. If you look closely, you'll notice that the preprint at the bottom and this middle preprint here actually appeared on arXiv on the very same day. So yeah, I encourage you guys to check out all of those references if you're interested in hearing more details about any of the stuff that I'll say in the talk. Okay, so let's sort of start out by giving a bit of an overview of what the goal of what I'd like to do in the talk actually is. So I'd like to describe a kind of generalization of the notion of quantum cluster variety. And the nature of this generalization is that we're going to replace the local pieces out of which the quantum cluster variety is glued by something a little more non-trivial. So in the standard setup, which we'll review in details later on. So just to take this as kind of motivational for now, but these quantum cluster varieties are glued from some very simple non-commutative algebras called quantum tori. The generalization that I hope to explain is one in which these quantum tori are replaced by some more interesting algebras called skein algebras of surfaces. So that this might seem like a very strange thing perhaps to want to do. And the way I want to kind of start the talk is really with the motivation for considering such construction in the first place. And where that motivation comes from is that we'd like to use this upgraded skein cluster structure to compute some kind of enumerative invariance for real three-dimensional Lagrangian submanifolds in Kähler C3. So what are these enumerative invariants? Well, they're the open Gromov-Witten invariants for such Lagrangians, but in the skein-valued sense introduced by Tobias Ekholm and Vivek Shende. So what I want to do, to begin the talk, is to say some very kind of general things about this setup of skein-valued open Gromov-Witten theory, motivate hopefully why it's a natural thing to consider in that context, explain what are skeins, and then kind of to zoom back down to concrete things and talk about quantum cluster algebras and their skein analogs. So somehow maybe it's pedagogically backwards. We'll start very kind of high level in general, and then zoom down to concrete technical details as we go on. Okay. So what is this skein-valued open Gromov-Witten theory in the sense of Ekholm and Shende that I just mentioned? So the setup is we have some Kähler threefold. So for us, it will always just be Kähler C3. And we're inside of that threefold, we're interested in real Lagrangian submanifolds. So given that this is the M seminar, it seems appropriate to mention that in the physics parlance, these real Lagrangians L are called branes. And so the idea of the open Gromov-Witten theory is that we would like to, in a certain sense, count holomorphic maps from Riemann surfaces into our threefold X. But in contrast to the usual story, these Riemann surfaces are allowed to have a boundary. And this boundary, its image under the holomorphic map is required to lie in this real Lagrangian submanifold L. So the boundary of the Riemann surface is mapped into our brane L. And of course here, it's not so obvious what count means, but as usual, it involves some version of integration over an appropriately compactified moduli space of these holomorphic maps.
I guess may I interrupt you?
Yeah.
So in what generality this open count is established?
Right. This is a very good question. So, I think in work of Ekholm and Shende, they establish it in the framework of any what they call open Gromov-Witten theory, in which SFT stretching holds. And then I believe there's an in preparation work of Ekholm and Shende establishing an example, well, a construction, an explicit setup and verification that SFT stretching does hold. So I think
but kind of since I did not read the paper,
yeah.
So X is non-compact, in particular
Right.
C3 is so it's non-compact
right.
scalar, and probably there should be some conditions at infinity at least, and L is also non-compact.
That's right.
So then there should be some other conditions at
Right.
infinity, and so kind of I am outdated in that topic, but at the beginning of the story, which was miles ago by, I believe, by Sheldon Kantz and Melissa Leo, they struggled with some analytic problems to make sense of this moduli space, not mentioning its compactification. So then for which Kellers and Lagrangians, like certainly a resolved conifold and Lagrangian dual to the zero section, and T star of S3 should be an example. And what generality, it's kind of, it's done mathematically.
So I feel very unqualified to make a proper statement about the exact generality in which, in which these things are actually currently rigorously defined. But if any more learned
for C cube, like it's already non-compact.
It's already non-compact. That's right. Yeah. So for the Eigenalgebraic buffer for the toric brane in C3, which is the original case of Katz and Liu, they are well defined by that work, and as you say, also for resolved conifold. And the class of branes that will be relevant for what are we talking about are basically ones you get by gluing together these Eigenalgebraic toric branes in an appropriate way. And what makes the story sort of much less tractable, at least using the original kind of technique of Katz and Liu, is that you no longer have a torus action when you glue these things. So you can't use localization in the same way that they did. So
and the torus section will be what in the case of C cube?
So the torus section is not so much about C cube, but rather on the L.
Oh, okay.
Yes. So that's where. So the issue is with the class of L that one. Yes. So the problem is you fix X and you fix L, and regard that as.
Okay, so it's kind of not clear for me, but go ahead. Yeah.
Yeah, I agree. This is right. This is also an aspect of the story that I don't understand particularly well and would like to understand better. But yeah, the aspect I want to kind of focus on is more of an I suppose more of an algebraic nature. In other words, like taking this as motivation to try and introduce some new kind of algebraic structures analogous to cluster varieties. But I agree, it's a very good and important question, the extent to which these counts actually make sense. Okay. So, right. So yeah, again, on this topic of the analytical problems that are involved in defining such a count, the basic issue is that, I suppose it's one that shows up even in the usual closed case, is that the definition of these counts depends on some choice of sort of perturbation data, which roughly speaking consists of wiggling this moduli space so that it's actually cut out transversely in an appropriate sense in the space of all maps. So there's some continuous choice of data that's involved in doing this perturbation. And we'd like to know that the counts we get actually don't depend on that choice of perturbation data. And in the closed case, that's indeed true, but unfortunately fails in the open case. So in other words, we can have families as we vary this perturbation data, families in which we have the boundary of some curve developing a nodal singularity. So to read this picture at the bottom of the slide, imagine we have some point in our family, maybe for, let's say, a negative value of time here, where this northeast component is above the northwest one. Then on the other side of our kind of singular point, we have the other way around. And the two counts on either side of that kind of critical value, those two counts don't agree. And in fact, but the way in which they differ is quite well controlled. Namely, it corresponds to some multiple of this resolution that you see in the right-hand side.
So again, a bit confused. So you have this relative homology class for your pseudo-holomorphic disks, disk with respect, okay. So then part of the boundary component is when this boundary curve is no longer smooth, but its class satisfies this skein relation.
Yeah.
Okay.
Right.
And Q is related to...
Yeah, Q is, right. So H is the usual genus counting parameter, and Q is is exponential.
All right, so H is roughly the area of whatever.
Right.
Okay.
Precisely. Yeah. Okay, so yes, so this really is the main insight of Ekholm and Shende, is that this kind of failure of the deformation invariance is not a total disaster, but in fact is an interesting structure in its own right, and one that is familiar to kind of not theorists and low-dimensional topologists, namely is what's called the HOMFLYPT skein relation. And so yeah, the slogan for this approach is this skeins on branes yoga. So the upshot is that you do in fact get a deformation invariant count. So deformation invariant open Gromov-Witten partition function.
What is O?
What?
OGV, I understand Gromov-Witten last...
Open.
Open,
Yeah.
okay.
O for open, yeah, sorry for...
it's not the last name, okay, good.
Yeah, that's right. Yeah, so the upshot is that what we need to do is to count these maps valued by the class of the image of the boundary in what's called the HOMFLYPT skein module of the three manifold, giving the boundary condition. So what is this HOMFLYPT skein module? Well, you take isotopy classes, you take the free module on isotopy classes of curves, of links in your three manifold, and then you impose the following relations. So one is this relation at the top that we just discussed, saying that the difference of these two crossings is proportional to their resolution. And then there are another two relations. One saying that you can resolve a kink, like this one shown at the bottom left, at the cost of multiplication by some parameter A. Yeah, and I guess I neglected to mention that this HOMFLYPT skein module is a vector space over rational functions in two variables that we'll call A and Q. So A, as you can see from this picture, is some variable related to framing, and Q is as we've seen. So we have this relation about resolving a kink, and then we also have this normalization type relation saying that the unknot is proportional to the empty link, which is what's on the right-hand side. Okay, so this is the HOMFLYPT skein module associated to a three manifold. So let's kind of introduce the simplest possible example where the three manifold is R3. And in this case, it turns out that in fact the HOMFLYPT skein module is just the one-dimensional vector space spanned by the empty link over rational functions in A and Q. And so here I've had a terrible choice of notation. So I should use some sort of lowercase l or something, because I'd previously been using L for a three manifold. But anyway, if you have some link, say little l, in R3, then under this isomorphism, this link is sent to some function of A and Q called its HOMFLYPT polynomial. Okay, so that is the HOMFLYPT notion of HOMFLYPT skein module. So in the case that we have a three manifold of the form surface cross an interval, then in fact this HOMFLYPT skein module has a bit more structure than just a vector space over this ring of rational functions. In fact, it becomes an algebra over that vector space, just by, so to speak, stacking cylinders, coming from the inclusion of two small intervals into a larger one. That map induces an associative product on the skein algebra for surface cross an interval.
Sorry, this skein module from the previous story, it's defined for a fixed three manifold.
Precisely, yeah, that's right.
And this three manifold, I mean, it's invariant with respect to homotopy of the manifold.
That's right.
Yeah. All right.
Good. Right, and it carries an action of the mapping class group of the manifold as well, because we started with isotopy classes of links and then imposed some relations which are indirect.
Yeah, in the previous slides you mentioned about the HOMFLYPT polynomial. So is it true that inside of R3 all links, the value corresponding is always a polynomial of A and Q?
If you set the normalization up correctly, then yeah, you get a polynomial. It depends on how the unknot gets to be normalized. It's a good question, as usual with this stuff.
Thank you.
Good. Okay, so yeah, as we said, if we have a surface cross an interval, then the skein module is in fact an algebra, just by stacking of the interval direction. And yeah, in much the same way, if we have a three manifold whose boundary is the surface sigma, then the skein module of that three manifold, it's not just a module over functions in A and Q, it's a module over the skein algebra of its boundary across an interval, just by stacking onto the boundary.
So,
So
and usually people speak about skein algebra of this surface sigma.
that's
this-
right.
Yeah, okay.
Yeah. Yeah, so often this will just instead of writing sk of sigma cross I, we'll just get abbreviated to sk of sigma with the understanding that in order to make a three manifold, you just cross. Yeah, and I'll probably lapse into writing that later on in the talk. So, yeah. Okay, so right, so with this sort of extra structure, we can come to a kind of second concrete example. Which is the skein algebra of the two torus. So skein of T2, again, that means we take skein of T2 across an interval. So there's a very nice presentation of the skein algebra for this two torus. It was worked out by Hugh Morton and Peter Samuelson. And it looks the following way. So let me just say first the algebraic presentation and then explain what skeins actually correspond to the generators. So the generators, we have one generator for each vector, integer vector in Z2. So for each such x, we have a generator P sub x. And the relations have this very nice form that the commutator of Px and Py is proportional to P of the sum of x plus y. And the coefficient of proportionality is q to the determinant of the matrix xy minus q to the minus determinant. Okay, so yeah, for those familiar with these quantum groups of elliptic Hall algebra type, you'll notice that this is the q is equal to t specialization, again, an appropriate kind of closed unit, so to speak, of the elliptic Hall algebra.
Yeah, I have actually two questions. First,
Yeah.
in general, this skein of a surface, can it be defined intrinsically in terms of certain curves belonging to the surface, entirely to the surface, yeah, without going to three dimensions? I remember Turaev many years ago define something using the intersection indices on curves and this kind of stuff.
Yeah, I guess I'm not aware of such a
Maybe I somehow forgot because it was in a different, historic period. All right, and second question is with too many Qs. To define the elliptic Hall algebra, you need, well, it depends what do you call elliptic. Do you work over finite field? Then the finite field has its own Q, so I'm kind of confused. In the end, it does not, but originally Q has kind of a meaning. It's a number of points in the finite field.
That's right.
Yeah.
Yeah. So yeah, but by this I mean right. So that original construction from the whole algebra of elliptic curve produces you some relations, and then one takes those relations and uses them to define an algebra over rational functions in Q and T. So and that is what I mean by this symbol epsilon Q T. So
yeah. Okay, I understand. Yeah, and in relation to my previous question, I see the picture on the same scale corresponding to MN curve, which means that indeed a curve on your surface gives rise to a skein. So then,
yes.
Probably it can be described entirely in terms of closed, probably curves.
Right. So yeah, exactly. So from these relations, we see that we can generate using the simple closed curves. But yeah, so that's an excellent point. So what are these generators Px, Py in these relations, right? So it's easiest to define them when the entries, let's call them m and n of the vector x, are co-prime. So in that case, by doing an element of SL2Z, mapping class 2 with the torus, we can just bring them to, 1, 0. And in that case, it just corresponds to a simple closed curve on the torus. And by embedding the torus into the torus across the interval as some slice, we get a skein we get an element of this skein algebra, skein of T2. So yeah, when M and N are co-prime, there's no ambiguity. PMN just corresponds to the MN curve on the torus. On the other hand, if we have some two-component vector, M, N, where the entries are not co-prime, so for instance, we have some skein of the form P, K, 0, again, using the change of basis in the lattice, it's enough to just consider this case and get all the rest by change of basis. So what are these elements corresponding to K, 0 as our vector X? Well, these elements are produced using some very interesting piece of structure on the skein algebra of an annulus. So the idea is we have our simple closed curve, let's say 1, 0. It lives inside some annulus, so some local annulus. And on this skein algebra of the annulus, there are, in fact, Adams operations. So how do these Adams operations work? Let me first give a very concrete explanation just with pictures and explicit formulas, and then say some words about why they should exist at all. But yeah, first, to be very concrete, right? So now imagine we have some curve which, if you were to draw it just flat on the torus, it won't necessarily be self-intersecting, right? So then what do we do? Well, we consider these skeins that in this picture are called A, I, J. So we have all of these intersection points. Here, I guess we have 6 of them. And for each way of writing 6 as a sum of 2 natural numbers, we consider an Aij, where first we have I overcrossings, followed by J undercrossings. Right, so in other words, we have to, if we just draw the thing flat on the torus, we have self-intersections, and these Aijs are ways of resolving those self-intersections inside the torus cross the interval. Okay, so
is there a kind of Hopf algebra structure on the skeins?
So that is a good question. So what I'll say in a minute is that you should think of this skein algebra of the annulus as some kind of n goes to infinity limit of the center of the quantum group UQ of GLN. So certainly there is a Hopf structure in the background, namely that of UQ GLN, but the center is not. It is not in any sort of sense Hopf subalgebra there. So yeah. Any other questions about this definition of these generators corresponding to non-simple closed curves on the torus? Okay, so right. So here's some explicit picture that defines for you what these things are. And as I was mentioning, the reason why you should expect for the skein of an annulus to have something like Adams operations is that it, in a certain sense, is the limit as n goes to infinity of the centers of the quantum groups UQ, GLN. And there's a construction of a nice construction of elements of the center of quasi-triangular Hopf algebra, like UQ, GLN, where what you can do is you can take the R matrix from that quasi-triangular Hopf algebra, multiply it by its opposite, and then take the quantum trace. So in other words, this is like in some sense, and take the quantum trace over one leg of the resulting thing in your favorite representation. So if we take the trace in the defining representation, then we get some element of the quantum group, because the R matrix lives in quantum group tensor quantum group. We take the trace over one factor, we end up in the quantum group, and the statement is that the resulting element is central. Okay. And so what these elements pk, 0 correspond to representation theoretically is taking the quantum trace over, say, the second leg, not of R21, R12, but rather of its kth power. So just like the usual Adams operation for, the representation ring of a group, which corresponds to evaluating the characters on the kth power of the group element.
Yeah, I think there is the Drinfeld construction for an arbitrary G, and so I think this product R21 by R12 is multiplied by some Q in the power of sum of all
precisely, yes.
roots. Yes.
Yes. So that's hiding in this. Yeah, I tried to sneak that into this.
I see. It's Q trace.
Yeah, exactly.
Okay.
You need to multiply by what in this case is effectively k to the rho. Yeah, where rho has some of the positive roots. Yeah. Okay, so yes, so that's the Adams operations on the skein of the annulus, and why you should expect them to exist from representation theoretic point of view. Okay, so yeah, so kind of as you might expect from this description as of the skein of the annulus as some limit over all n of centers of quantum groups. For each n, there's a reduction of the HOMFLYPT skein module. In other words, a quotient of it that corresponds to the reduction to UQGLN skeins for some fixed finite n.
What does it mean, UQGLN skein?
Yeah, right. So
you should color a link with a representation or something.
That's right. Yeah, and the links are colored with a vector representation. Yeah.
Okay.
Right. So yes, so there's a reduction for each n to some in some sense cruder skein algebra, and when n is equal to 1, this is a very crude reduction indeed. It loses a lot of information. Namely, it amounts to imposing an extra relation that allows us to completely resolve all crossings. So if we have some crossing like the one on the left, we can just resolve it at the cost of acquiring multiplication by this parameter q. So we just resolve all of the crossings, and the class of length depends in this linking skein depends only on the image in the first homology of the surface. Right. So, for example, if we look at the n is equal to 1 reduction of the skein algebra of the torus T2, then it will be generated just by two elements. Let's call them x and y, x corresponding to the 1, 0 curve, and y to the 0, 1. And they'll satisfy a relation, which I think I put the wrong sign on, right? Because, well, at least if we mean by 1, 0 to be the moving to the right one step in the horizontal direction and 0, 1 moving up, I think if I'd done it correctly, it would say that y times x is equal to q squared x times y. But I guess I also didn't specify my convention for the order of multiplication. That like whether x times y corresponds to stacking x on top of y or y on top of x. But, yeah. Anyway, is the picture clear and how this relation comes to be clear? So on the one hand, we resolve and we get q times xy, and the other way we resolve and we get q inverse times xy, and yeah, and that way the two products in either order, one is equal to q squared times the other one. Okay, so yeah, this quantum torus algebra is a very simple algebraic thing. It's just a kind of deformed group algebra of the lattice given by the first homology of the torus. Okay, So yeah, and of course the same is true of this linking reduction of the HOMFLY skein for a general surface. So if we have two links corresponding homology classes L1 and L2, then the product in one order is equal to Q to the 2 times the intersection pairing of those two classes times the product in the other. All right, so yeah, so now here's the idea of what I'd like to explain. So as we're about to see, there's an interesting kind of object in quantum geometry called quantum cluster varieties that are built by gluing together quantum tori, so for example, linking skeins of a surface, via some kind of gluing data called mutations. And so that the question is, can you also glue the full HOMFLYPT skein algebras, so not just their n is equal to 1 reductions to the linking skein, can you glue those full skein algebras in a similar way? And if so, can you use that structure to understand these Ekholm-Shende skein-valued open Gromov-Witten invariants? Okay, so yeah, so now I want to kind of make things extremely concrete in our discussion of cluster varieties and their quantizations and the skein analogs. So, and I want to explain these cluster varieties in, I think, the only way which is sort of possible or understandable, which is by means of example. So right, the main example that I want to focus on is a certain moduli space. We'll call it X PGL2S. And this moduli space parameterizes what are called framed PGL2 local systems on a surface with punctures. Right, so framed, so local system is just a principal PGL2 bundle on S with flat connection. And what does the framing data consist of? Well, the framing data is additional data near each one of the punctures of a flat section of the associated flag bundle in the neighborhood of that puncture. So locally near each one of those punctures, if we're looking in the fiber of our flag bundle, we have a point in P1, which is fixed by the monodromy around that puncture. So a line in C2 fixed by the monodromy in the fiber. So, okay, so this moduli space is, in fact, a nice rational variety, at least when S has enough punctures. And what do I mean by enough punctures? Well, I mean enough punctures to be able to draw what's called an ideal triangulation of S. So ideal meaning the vertices of the triangulation are at the punctures of the surface. So if we have such an ideal triangulation, then we can define a nice open set inside of our moduli space, which is defined by the condition that if we, for each one of our triangles, we look at the three flat sections of the flag bundle near the corresponding puncture, then we transport them to a common point, let's say in the middle of the triangle, and then we ask that those three lines be in C2, in that fiber, are distinct. And so so imposing that genericity condition for each one of our triangles cuts us out some open set inside of the moduli space. And that open set is just isomorphic to an algebraic torus of dimension equal to the number of edges of the triangulation. And so, in fact, it has that torus has a distinguished coordinate system with one coordinate for each edge of the triangulation. And the way that the coordinate x sub e associated to an edge e works is the following, right? So we have an edge in this triangulation. So it's an edge separating two triangles. So it lies in the interior of some quadrilateral, exactly one quadrilateral. And at the four vertices of that quadrilateral, we have four lines in C2, so 4 points in P1. And the value of this function is given by their cross ratio. Okay, so right, so now we have this moduli space of PGL2 local systems on S with a framing at the punctures. And inside of there, we can look at the subvariety where the local system, the underlying local system, has unipotent monodromy at each one of the punctures. Okay, so we ask if the eigenvalues of the monodromy are 1 around each puncture. And this turns out to be a pretty easy to describe subvariety. Namely, if we look at its intersection with each one of these charts corresponding to ideal triangulations, then it's just cut out by a bunch of monomial equations. So at each puncture, P, we just look at all of the edges incident to that puncture, take the product of all of those cross ratio functions, and ask for that to be equal to 1. And that is equivalent to the unipotency of the monodromy around that puncture P. So we impose those monomial equations for every puncture on the surface. So in particular, we just by intersecting with this unipotent subvariety, our original torus chart on the entire variety, we get another torus chart on the unipotent variety. So we've just imposed some linear equations effectively on our original torus. So this unipotent subvariety is also has a covering by torus charts corresponding to triangulations. Okay, so let me explain kind of an alternative description of these cross ratio functions that we just discussed. So it's kind of a dual description in the following sense. So we take our triangulation of our surface. So let's look, for instance, at this top part of the figure on the slide. So it's a bit of a confusing choice of example because in fact here the thing is kind of self-dual. But let's suppose that in black we've drawn our triangulation of the surface. So the vertices of the black graph are the 4 punctures on our surface. So we think of it as a triangulation of the sphere with 4 triangles, 1, 2, 3, and then 1 on the outside. So the dual graph to that triangulation is going to be a 3-valent graph, right? Because we glued together a bunch of triangles. And I've drawn that dual graph in purple. So that purple graph, let's call gamma. It's a trivalent graph, dual to the triangulation. And it has G plus 3 vertices, where G is so there's G plus 3 vertices corresponding to the triangles in the triangulation. So now what we can do is we can consider a double cover of our surface on which the original triangulation is drawn, branched over the vertices of the purple graph. So branched over the vertices of that dual graph. So in the example here, we have 4 vertices of the purple graph. The purple graph is drawn on the 2-sphere. And so we get a double covering of the 2-sphere branched over those 4 points, which is a torus, so a surface of genus 1. So in general, if our dual graph has G plus 3 vertices, the purple graph has G plus 3 vertices, then this double cover will be a surface of genus G that we'll call S gamma. So it depends, think of it as depending on the trivalent graph gamma. Okay, so edges, to briefly return to the picture, edges of the purple graph connect branch points on the base of the double covering. So they lift to loops, to cycles on this double covering surface S gamma, on this, so to speak, spectral curve. So in other words, for each edge of the purple graph, or equivalently to each edge of the black graph, we associate some loop on the spectral curve. And so then we can identify our algebraic torus we constructed from the triangulation with the first cohomology of this double covering surface with coefficients in C star, just by identifying the edge function, this cross ratio function, x edge with the loop corresponding to the edge of gamma, and we identify them as linear functions on the first homology, right? So on the one hand, we have this xc, which is a linear function on here. And on the other hand, we have this loop on which you can evaluate one of these cohomology classes. So in that way, we get an identification of these torus charts on the unipotent part of the moduli space with the first cohomology of the spectral curve with C star coefficients. So the first cohomology of this double cover with coefficients in C star. Okay. So why is this nice? Well, it shows us that each one of these torus charts has actually a holomorphic symplectic structure coming from the intersection pairing on the first cohomology. So the way that this Poisson bracket looks is that if you take the function corresponding to the loop corresponding to some edge ej, take this Poisson bracket with loop corresponding to the edge ek, then it's equal to the value of the intersection pairing on the corresponding loops on the double cover times the product. It's a typo here. It should be the product of those two functions. Okay. Right. So yeah. So far so good with this definition by example of cluster varieties. But what does the word cluster sort of actually refer to here? Well, what it refers to is the specific form of the gluing data between charts that are labeled by triangulations of our surface that differ by flipping just a single diagonal of a quadrilateral. So imagine we have two triangulations that are the same everywhere, except we have just one quadrilateral, which in triangulation delta looks as on the left, and in triangulation delta prime looks as on the right. So we have two, each one of those triangulations gives us an open set inside of this moduli space. And so we can ask what is the gluing data corresponding to their intersection, the intersection of those two open sets. And right. And so to describe this gluing data, it's actually nicer to kind of bite the bullet and first pass to the quantization of the entire cluster package for reasons that I'll explain in just a second. But what this quantization consists of, at least chart by chart, is promoting these coordinate rings of each one of these torus charts from commutative Poisson algebras to non-commutative quantum tori, where the direction of quantization, so to speak, is the one specified by the Poisson structure in the usual way. So in other words, to put it in the terminology from the beginning of the talk, the quantum torus corresponding to a given triangulation recovers the linking skein of the spectral curve associated to that triangulation. Okay. So what we're trying to do is glue together a whole bunch of linking skeins for each of these spectral curves corresponding to different triangulations of our surface. And so here's the way that gluing procedure works. Again, it's, I think, nicer to describe at the quantum than classical level. So what should the gluing be? Well, it should be some non-commutative birational isomorphism. So an isomorphism from the non-commutative fraction ring of the quantum torus associated to some triangulation delta with the corresponding fraction ring associated to the chart delta prime. And this gluing map consists of some very tame kind of linear part, which basically just comes from changing basis in first homology. But the interesting part is this nonlinear part. And the way that this nonlinear part works is that we take an element F in the quantum torus, and then we conjugate it by a certain formal power series called the quantum dilogarithm. So this quantum logarithm, phi q of x, there's various ways to think about it. One is as the following infinite product formula. So yes, so this is some formal power series. It's not an element of the quantum torus. It rather lives in some kind of completion. So a priori, the right-hand side of this expression is just some non-commutative power series. What is in fact true is that non-commutative power series is the series expansion of a non-commutative rational function. And the reasons for that is very simple, namely that, okay, here I've messed up my notations, but here psi should be phi. But the point is that, as you can easily see from this infinite product expansion, this quantum logarithm satisfies a difference equation. Namely, if you calculate phi q of q squared times x, that's equal to 1 plus qx times phi q of x. So you can see just from looking at that product. So in particular, that implies that these conjugations really do define birational transformations. For example, if you conjugate, if xy is q squared yx, you conjugate y by phi of x, then using the difference equation, you end up with y times 1 plus qx, not some random arbitrary power series. Okay, so a kind of alternative, I want to say a few more things about this quantum logarithm because it's really the key to the gluing data in the cluster story. An alternative description of it is as a plothistic exponential in the lambda ring in which q and x are Lion elements. And this description is perhaps explains why this thing is deserving of the name quantum logarithm at all. Because if we look at the logarithm of phi, then what we get is a series that looks very much like the, as q goes to 1, looks very much like the actual logarithm function. Okay, so, right. So, and of course, the key to the consistency of the gluing is the so-called pentagon identity for the quantum logarithm. Namely, if xy is q squared yx, then we have the identity that you can see on this slide. Expressing the product of logarithms in one order, two logarithms in one order as a product of 3 in the opposite. Okay, so let's now sort of bring things back to this open Gromov-Witten picture. So in the case that our surface S is a sphere with G plus 3 punctures, then it turns out that this quantum cluster structure, as we've just been discussing, captures the linking skein-valued open Gromov-Witten invariance for a particular class of Lagrangian branes in C3. So, so what is this class of real Lagrangian submanifolds in C3? For which we'll be able to say something like this. So the way that they look is as follows. So each of these spectral curves, so these double covers of the sphere branched over these G plus 3 points, each of these spectral curves can in fact be thought of as a Legendrian surface in the cosphere bundle to R3. And so then the Lagrangians, the real Lagrangians we'll be interested in will be fillings of that Legendrian surface. So if we're in this setup where we have our Legendrian surface S gamma corresponding to some cubic graph built from some cubic graph and some real 3 manifold L with boundary on S gamma, then this Ekholm-Shende partition function is going to be an element of the skein module of L.
Yeah, but I'm a bit confused with usefulness of the skein language at all. You have quantized some cluster variety, so you have quantum algebra, and you have a module of this quantum algebra, and Ekholm-Shende defined an element. quantum wave function, probably corresponding to some Lagrangian feeling or something. All right. So where are the skeins? I'm just
yeah, absolutely. Yeah. So far the picture I've described on the cluster side does not yet involve skeins. So I haven't yet introduced the skeins on the cluster side. But what I want to do first is explain the okay. So I haven't yet introduced skeins on the cluster side, except with this trivial observation that that when we reduce to the linking skein, we get quantum tori. So what I want to describe is a version of the story I just told for clusters, but where we don't reduce to the linking skein, where instead, instead of these quantum tori, we have the full HOMFLYPT skein algebra of the surface as our local non-commutative algebra that we glue together.
So then basically you should replace this quantum dialog by something
Precisely.
else.
Yeah. So that's the punchline I hope to be able to come to. So basically, yeah, exactly. The problem consists of finding the correct analog of quantum algorithm. Right. So, but yeah, returning to this, this setup of skein-valued invariants, a la Ekholm-Shende. So for each of these Lagrangian surfaces corresponding to a given triangulation and a Lagrangian filling that Lagrangian, then the wave function, aka the HOMFLYPT skein-valued partition function, satisfies a system of skein recursion relations. So yeah, this was worked out in the case of the toric brane, Akinoshi-Schwafer brane, and Resolve-Konefol in work of Ekholm and Shende. And then for these cubic planar graph Lagrangians, these skein recursion relations were computed by Schrader and Shende. So in other words, we have this partition function. We maybe don't know how to compute it, but we do know some kind of recursion relations that it satisfies. And when we do the reduction to the linking skein, those recursion relations are very simple to describe. They're just some Q difference equations for the partition function.
Are they homogeneous? I mean, do they determine the partition function uniquely or
exactly? So that's the key question, right? If those difference equations can be shown to have a unique solution, then to compute this Ekholm-Shende wave function amounts to finding that solution. So that's the important question, and that was not so it was clear in these Resolve-Konefol and toric brane cases, just from the extremely simple form of the recursion relations, but wasn't clear in the original paper of Schrader and Shende for a general cubic planar graph Lagrangian.
Yeah, so they are not homogeneous, yeah, in the sense that they do not have, they are linear with respect to unknown whatever function, because otherwise you can always multiply by a scalar, and you cannot define it uniquely.
Right. Yeah. It's a good point. Yeah. So unique. When I say unique, I do mean unique up to multiplication by a scalar function, because of the
but you cannot multiply the partition function in the string theory by a scalar, because
exactly,
it's
yes.
indeed unique.
So that's the point. The partition function has to start with 1, right?
It has to start with something, but if it's just abstract system of Q difference equations,
right.
Yeah.
Yes. So the correct uniqueness statement is that abstract system of Q difference equations has a unique formal power series solution of the form 1 plus terms of order n.
Okay.
But you're absolutely right. It's homogeneous, so you can, of course, if you don't care about that normalization, if you don't care about interpreting it as partition function, then you can multiply by any scalar function of Q. Yeah. So, right. So the basic idea from this first preprint with Lin Hui-Shen and Eric Zaslow that I mentioned at the beginning is that for the linking skein-valued counts, these systems of Q difference equations for different pairs consisting of a cubic planar graph Lagrangian and Lagrangian filling. So those different pairs, they define different enumerative problems, but nonetheless, you can glue them together to define a global quantum holomorphic Lagrangian submanifold in this quantum cluster braid. So what is this? Semi-classically, what is this? Is this Lagrangian submanifold? Well, it's very simple to describe. So remember that the cluster Poisson variety is parameterizing these framed local systems on the punctured sphere with unipotent monodromy at the punctures. And so inside of that moduli space, we can look at the locus where the underlying local system is actually just trivial. Not just unipotent monodromy, but in fact just trivial local system. So what that means is that the only data that remains is that of the framing, right? So the choice of these invariant lines in C2 at each one of the punctures on the surface. And because the local system is trivial, we can pick the condition that it be monodromy invariant. The line we choose is just vacuous. We can pick any line we like, right? So this locus we can consider inside of our moduli space. It turns out to be a holomorphic Lagrangian submanifold cut out by explicit defining equations. And to see what those defining equations are, it basically follows from the following description. Namely, if we take the intersection of this locus M, where the monodromy, or where the local system is trivial, we intersect it with a torus chart corresponding to some cubic graph gamma. So then the moduli space M just, this locus M just parameterizes all ways to color the faces of gamma by elements in P1, so that that if we have two faces separated by an edge, we color by a distinct element. So usual sense of graph coloring, but by elements from P1. For that, in view of that coloring interpretation, we call this global locus M the chromatic Lagrangian. This intersection with any chart parameterizes graph colors.
Yeah, I'm wondering if you rotate the complex structure, so then your local systems become kind of holomorphic. This Lagrangian, no, maybe I'm wrong, because you say that it's holomorphic in the complex structure associated with something like character variety.
Exactly, so, the Betti character variety, yeah.
Yeah, so it certainly is not related to operas in any way.
No, I don't think, yeah.
Yeah, okay.
Right, so we have this global holomorphic Lagrangian, and we can describe explicitly its intersection with any one of these torus charts in terms of a modular space of graph colorings. And so yeah, just to kind of summarize this, I guess, verbal discussion from a few slides ago, combining the results of Shende on the difference equations, the existence of Q difference equations satisfied by the partition function, and our results with Eric in Lin Hui, we obtained the following theorem, namely that for the reduction to the linking skein, these systems of Q difference equations satisfied by the open Gromov-Witten partition function associated to different toric charts glue together under quantum mutation, as we described, to define a global representation of the quantum cluster braid. For certain, under the certain kind of mild technical restrictions on the Lagrangian surface and Lagrangian filling, that corresponding system of that corresponding system of Q difference equations as a unique power series solution of the form 1 plus order X. So the upshot is that we can use the quantum mutation to relate solutions of different enumerative problems corresponding to different graphs gamma and different fillings L. So yeah, I want to kind of, what time is it? Should I stop? Yeah.
Well, you can continue for a while. So
Okay. Maybe like 5 more minutes is okay?
Yeah, absolutely.
Yeah. Okay, thanks. Cool. So, right. So I want to kind of explain this. So again, the logic is we know some difference equations satisfied by the partition function. We now know they have a unique solution. And we now know that we can relate these systems of equations for different enumerative problems by mutation. And that turns out, in fact, to allow one to write explicit formula for their solution in the following way. So yeah, let me try and explain it by example. So this example is this Agenaki-Schwafer toric brane in C3 that we mentioned right at the beginning. So yeah, in this case, the underlying cubic graph is this tetrahedron graph on the sphere. So the spectral curve is a torus, T2, and this corresponding Lagrangian filling is a solid torus. In this case, again, as we've seen, the completed appropriately linking skein of this solid torus is just identified with completed group ring of the first homology of the solid torus. So just power series in X with coefficients depending on Q. And so that linking skein of L is a modulo over the linking skein of the 2 torus, which again, as we've seen, is this algebra generated by X and Y with this simple Q commutation relation, and unwinding what the natural action of the skein of T2 on the skein of L means in terms of this, this identifications, we see that the element Y acts on a function of X, so some element in this completed linking skein, by just dilation of the variable X by a factor of Q squared. So in this case, the difference equation for the partition function has the form y minus 1 minus q times x, acting on the wave function is equal to 0. So its semi-classical limit is this pair of pants sitting inside of C star cross C star. Okay, so in this Agenaki-Schwafer case, which remember corresponds to the tetrahedron graph and this pair of pants difference equation, we can consider what happens to the difference equation when we do a single cluster mutation. And the one we'll do corresponds to flipping this edge here of the tetrahedron graph. When we do that, we get this. And I should mention that why did we choose this edge here? Like, what is special about this edge? Well, this edge here corresponds to the the homology class of the generator X for homology of the solid torus L, right? So we'll mutate there and obtain this necklace shaped graph on the right. So this necklace graph on the right, if you apply the same construction of building the corresponding Lagrangian surface and its Lagrangian filling, then that Lagrangian filling is in fact, an exact Lagrangian filling. It's this Chikhanov torus. So its partition function is just the trivial one, just equal to 1. At the level of quantum mutations, we see that this corresponds to the mutation of the system of difference equations on the left. So the ideal generated by this difference equation on the left, we mutate, becomes this trivial almost difference equation 1 minus y is equal to 0, which of course just says that the function doesn't depend on x because dilating x by factor q squared preserves the function. This is sort of a toy example which shows that one can solve this difference equation on the left by mutating back to a trivial difference equation. And effectively, because any two triangulations can be connected by some sequence of flips. This allows you to compute more or less all of these partition functions for the cubic planar graph Lagrangians by applying an appropriate sequence of quantum mutations to this trivial Plekhanov waveform. So yeah, again, I guess what I just said is that we solve this quantum difference equation by mutating it back to a trivial one. Okay, so yeah, let me now really try and finish by explaining how to extend this results we just discussed from this rather trivial case of the linking skein to the full HOMFLYPT skein algebra. So, right, and as Jan observed probably half an hour ago already, that the main ingredient needed to do this is a skein analog of cluster mutation, which would allow us to make sense of how to glue the skein modules corresponding to different qubit graphs. Right, so now, so again, if we have some edge of the qubit graph, it corresponds to some simple closed loop on this double cover surface S gamma. And again, that simple closed loop will be contained in some annulus inside of S gamma. And so we can apply these atoms operations for the annulus skein that we discussed right at the beginning of the talk, the ones corresponding to this, nth power map, so to speak, in the quantum group description, in order to define skeins corresponding to, well, for any natural number, P of n times our edge that we're trying to flip. And then finally, we can come to the main definition of the talk, which is a skein logarithm. And again, the definition exactly mimics the standard quantum logarithm, except rather than working in this lambda ring where we just have a line element x in addition to our line element q, now we have this atoms operation that sends, so the nth atom operation sends x to n times x. So we get a formula like this, which lives in appropriate completion of the skein algebra of the spectral curve, the full HOMFLYPT skein algebra of the spectral curve. And so we can use conjugation by that element to define a notion of skein mutation and glue together the HOMFLY skein algebras for mutation equivalent graphs. So just to finish the theorem from this preprint with Wu and Zaslow is that the full HOMFLYPT Shende skein recursion relations satisfied by their partition function do indeed glue compatibly under this notion of skein mutation. And for the same class of Legendrians and Lagrangian fillings as in the rank 1 case, those recursion relations have a unique solution, which we can compute by iterated skein mutation back to the trivial Plekhanov wave function, which is just given by the MB length. Yeah, so I think that's probably, I'm sort of, well over time. So yeah, let me stop there. Thanks.
Yeah, all right. Thank you very much. But still I kind of missed, so the main advantage of this skein language is that you have sort of invariance with respect to changing one Lagrangian filling by another one and get some simpler system of equations or something like that.
Yeah, so I would say that the advantage of the skeins is that they allow you to define some kind of deformation invariant count in the first place under some kind of in some kind of appropriate settings. So the skeins you should think of as being attached to each cluster chart. So to each qubit graph, there's a corresponding spectral curve. It has a skein algebra. If we have a filling, a Lagrangian filling, then we get a module over that skein algebra. And there's an open Gromov-Witten partition function living in that module, which is annihilated by some operators. And so what the virtue of, in some sense, what the virtue of the clusters do is that they let you relate different Lagrangian fillings of different Legendrians. So they allow you to relate enumerative problems by which you can replace a relatively complicated one like this one for the Agenacci-Schwaffe brane by a much simpler one like this one for this Kirchhoff torus. So I'd say, yeah, there's somehow two directions of, two kind of novel directions. One is this Ekholm-Shende idea to work with skeins, which is related to the deformation invariance of the counts. And then there's this other idea that there's some kind of cluster structure relating different enumerative problems for these open Gromov-Witten invariants.
Yeah, cluster, I understand the cluster part, but the skein, it's kind of, and also, it's a sort of a very general question. So, there is this business of categorifying monoidal and not necessarily even monoidal categorification of cluster algebras. I'm just curious whether it's upgradable to skeins.
Yeah, it's a very good question. Yeah, right. So, I'm also very curious about this because, yes, so the skein algorithm also, I sort of ran out of time to say it, but it also satisfies a pentagon relation, much like the standard n is equal to 1 quantum dilogarithm. So yeah, we proved this in the paper for the skein of the closed torus, but it was then subsequently significantly improved by Mingyuan in that he showed that pentagon equation holds in the skein of the punctured torus, which describes the tubular neighborhood of a pair of curves intersecting at a single point in just a general surface. But yeah, somehow this pentagon identity, that definitely makes one think of this kind of categorifications and stability conditions and wall crossing. But yeah, I think that's largely unexplored at the moment.
Yeah, also another question. Last week we heard the talk of Safronov, who also mentioned skein modules. And so he said that if we go to from module defined over rational functions, so even over Laurent polynomial, but all the way to formal series, then they can be, the skein modules can be defined in a completely different way using not rather the conventional whole algebra business, but using this cohomological whole algebra, cohomology of some space with coefficients in the sheaf of vanishing cycles. And I do not see any relation of what he said to what
that's interesting. Yeah, I'll have to watch his talk. Yeah.
I think he has a paper with Gunningham. That he was talking about.
Yeah.
Because you mentioned elliptic whole algebra, it's just usual whole algebra, but there is a cohomological whole algebra. And they're different, but still can be related because in the end they give the same invariants, this generating functions and quantum dialogues. Yeah, and another thing, it's sort of, maybe it's a question. You used kind of a very simple skein algebras associated with surfaces. But basically they are generated by some closed curves. For example, for the torus, it kind of they generated by geodesics, by minimal. All right, but then you can instead consider the Fukaya category of the surface for the torus, for the symplectic torus. I think maybe K0, you get the same elliptic whole algebra.
Yeah, that's right. Yeah, I think there's some work by, is it also Peter Samuelson? And
maybe I don't know. Yeah, I mean that it's K0 of the Fukaya category, the Grothendieck group. Can it do as well as a skein algebra of the surface?
Yeah, that is.
Of course, surface is not quite, I mean, you should be careful in defining the Fukaya category, but in many cases, people kind of can say, what is it?
Yeah,
so,
it's a good question. Yeah.
Yeah, I think, and maybe the last question, this Shende, Ekholm-Shende generating, you know, there is a notion of num-sum, Werner num-sum.
Yeah.
Since Reshetikhin is there, so Reshetikhin-Turaev invariants and nums. So is this generating function given by this kind of a sum, num-sum?
So remind me the definition what this.
Yeah, I mean, it's basically, it's a sum with coefficients which are quotients of quantum factorials, so roughly speaking, or they can be quantum binomials.
Yeah. So see, yeah, this kind of gets to an interesting point, right? Because in order to, in the general skein case, in order to think about, say, coefficients of this generating function, it kind of depends on the choice of a basis in the skein of the three manifold. And of course, if you pick different bases, you'll get different coefficients. And so it kind of, something that I don't understand well at all is what the kind of natural or appropriate choice of basis to make is. And yeah, in particular, one could ask if these wave functions have this kind of integrality properties like they have in n is equal to 1. So when n is equal to 1, they're really, you can really just think of them as power series in number of variables. And it follows just from this description as iterated mutation that they satisfy the sort of Uguri-Vafa integrality property, and integrality in your sense with Maxian. Yeah. So, but yeah, I don't even really know how to formulate such integrality notion in the skein setting, because it seems to depend on the choice of the basis. But...
I see. And do you, I mean, you defined it over rational numbers. That's maybe not the best, so you cannot specialize to roots of unity.
Exactly. Yeah, exactly. It's a very good question about what happens at the roots of unity. I think this understanding of the skein algebras at the roots of unity is a rather difficult thing. So yeah, but that probably
at least for the torus, at least for the torus, you can do this. Yeah.
Yes, for the torus it can be done. Yeah.
Okay.
But I think even that it's sort of not entirely clear to me that there's like a basis, an integral basis for the
no integral basis. It's maybe this, this Safronov story, because for cohomological whole algebra there are some integrality results, but still I don't know. I haven't thought about it. Yeah. All right. More questions? Well, okay. If there are no questions, so thanks again. Very nice talk.
Thanks for having me. Thanks, guys.
Thank you. And so this is it. Bye-bye.